Hello students, welcome to the second part of our second module in compressible fluid flow. Students, in the first session of our second module, we have discussed the idea of isentropic flow. We have discussed the various Gaussian equations, how to represent the isentropic flow process on a Muller diagram, and we have discussed the concept of flow expansion and compression, how expansion is different from compression and how they are depicted or they are plotted in a Muller diagram or HS diagram. Okay, so students, now today we will learn about the effect of area variation. how variation of area in the flow conduit affects the flow, affects the properties of flow. Okay, so students, suppose this is my flow conduit. Okay, so I am taking a small control volume here. Okay, control volume. So this is some section 1, this is section 2. Let the flow be m dot, and we are considering only a steady flow, so m dot remains constant. The students, here let the area of cross section at 1 be A, pressure be P, and density be rho, and enthalpy be H, and temperature be T. Okay, so here area has got some change, right? So A plus dA, I'm marking it as A plus dA, P plus dP, pressure, density rho plus dou rho, temperature T plus dt, and enthalpy H plus dH. Okay, so this is a variation. So I am considering a small control volume. This is my control volume, and this is first section, this is second section. The values of various values of properties at one first section are this, and in second section are this. Okay, now I'm going to derive some the equation for effect of area variation. Students, you know continuity equation, rho a velocity equal to constant. So I am taking logarithm of rho av equal to log c, right? Yes, log of rho av can be written as log rho plus log a plus log v. Natural log v equal to another constant. Log c is also a constant. Okay, so I am differentiating it. I am differentiating it d log. Our equation was log rho plus log a plus log v equal to some constant, right? So if I am applying differentiating, if I have differentiated, so the differential form will be d rho by rho. Since the log rho means if you differentiate rho, it will be d rho by rho, right? And it will be dA by A plus dV by V, and if you differentiate a constant, this is V, and if you differentiate a constant, it will be 0. So this is the differential form of our continuity equation, right? Differential form of continuity equation. Keep it here. 1. Now our enthalpy equation or standard steady flow energy equation is H plus V square by 2 is a constant, right? If you differentiate it, the differential form will be dH plus 2V dV by 2, right? So 2 and 2 cancel equal to 0. It means 2V dV. dH plus V dV equal to 0. So this is the differential form of energy equation. Previous equation was the differential form of continuity equation. Right, students, you know from thermodynamics, TDS, you have learned TDS equations. TDS equations dH minus VdP, small VdP, where small v is specific volume, not velocity, specific volume. specific volume, right? So you might have learned, you might be remembering this equation, right? So since here in our case it is isentropic flow, so ds will be 0, right? It gives dh equal to small v dp, right? So small v is always the inverse of small v will be equal to 1 by density. So our equation can be written as dh equal to dp by rho, dp by rho. Okay. So I am substituting this equation 3 in substitute 3 in 1. This 3 in you just substitute in 2, 3 in 2. So what was our second equation? Second equation was this one. So I am substituting this for dh I am substituting dp by rho. Okay, so dp by rho equal plus v dv equal to 0, right? So students, you will get dv equal to minus dp by rho v. So I am getting an equation for dv. So this equation is 4. Okay. Now I am substituting 4 in 1. So what was our first equation 1? The first equation is dou rho by rho plus dou a by a plus dou v by v equal to 0. I am substituting for dv. So dv can be substituted with this value minus dp by rho v. So the equation becomes d rho by rho plus dA by a minus dp by rho v, rho v, and one more v is there, so rho v square is equal to 0. Okay, equal to 0. Now I require, we are actually aiming, our objective is to find the effect of area variation of the property. So area variation, this is the term for area variation, dA by a, change in area by original area. Okay, so I am taking that to, I am keeping that in left hand side and moving all other terms into right hand side. So the equation becomes dA by a equal to some dA by a equal to dp by rho v square minus d rho by rho, right? So dA by a equal to I am taking dp by rho v square as common, and what remains is 1 minus v square is there, and d rho by dp remains, since because I have taken dp by rho v square common, right? So what is this? Do you remember? You have already studied the equation for acoustic velocity. Equation is nothing but root of dp by d rho at a constant entropy, right? Since our process is at constant entropy, our process is isentropic process, this will be at constant entropy itself. So this gave d rho by or a square is nothing but dp by d rho, right? dp by rho. So this is d rho by dp. So it will be 1 by a square. Okay, it will be 1 by a square. So dA by a equal to dp by rho v square into 1 minus v square by a square, right? So what is this? V square by a square, it is nothing but max square. dA by a equal to dp by rho v square into 1 minus max square. So I am rearranging this equation to a better form. dA by a equal to 1 minus max square by rho v square into dp okay. So change in area by original area is equal to 1 minus max square by rho v square into dp. So this relation is the relation between change in area with the change in pressure. It is a function of Mach. Okay. So you just keep this equation. This is a very important equation which can be used for various study. So keep this equation. Now, students, you have already found an equation called relationship between dp and what is that equation? Okay, so here you have an equation called an equation or a relation between dp and dv. So students, dp is nothing but equation 4. Equation 4 is nothing but dv equal to minus dp rho v, right? Minus dp rho v. So this equation 4. So dp can be written as dp can be written as minus rho v dv. Minus rho v dv. So substituting this here, what will the equation becomes? dA by A equal to 1 minus max square by rho v square into rho v dv minus, okay, minus. So this rho cancel, v cancel. So it will be max square minus 1 by max square minus 1 by dv by v. So dA by A equal to max square minus 1 by dv by v. Very important. So this is so mark this as equation 5, mark this as equation 6. So what is the difference between equation 5 and 6? Equation 5 relates dA by A with the dp, okay, and equation 6 relates dA by A with the dv. So change in velocity with the change in area, change in pressure with the change in area. Okay. Now another equation, since so students, here the equation of dp, take equation 5. In equation 5, dp can be substituted with a square d rho, right? Because dp by d rho is nothing but a square. So I am substituting here dp with a square d rho. Students, what will the equation become? dA by A equal to 1 minus m square rho v square into a square d rho. So a square by v square is nothing but 1 by max square, right? 1 by max square. So it will be 1 minus m square by m square d rho by rho. So dA by A equal to, so students, this equation relates dA with the d rho, the change in area with the change in density. So we have got 3 equations relating dp with dA, equation relating dA with the dv, and equation relating dA with the d rho. So these are the various equations relating pressure, change in pressure, change in velocity, and change in density with the change in area. Students, what is actually a nozzle? A nozzle is a device employed in a flow passage to gain velocity at the velocity increase, to gain velocity increase at the expense of a pressure, at the expense of pressure, expense of pressure. So students, nozzle is a device used to increase the velocity of a flow by use at the expense of pressure. It means while flowing through nozzle, velocity will increase, pressure will decrease. Due to the decrease in pressure, velocity should increase. So such devices are called nozzle. What is diffuser? Diffuser is another type of component, or a device employed in a flow passage to gain pressure, increase at the expense of velocity. That is the difference. At the expense of velocity. So while flowing through a diffuser, the flow in the diffuser must be such that as flow proceeds, the pressure of the fluid increase, velocity decreases. So this is the basic difference between a diffuser and velocity. So in case of a nozzle, velocity should increase? Velocity increase means dV by V should be positive and dP by P should be negative. Okay, in the direction of flow, this should be the gradient. dV by V should be positive, that means velocity increase. dP by P should be negative, that means P decreases. So here students, pressure increase. So dP by P should be positive, dV by V should be negative. Okay, so that's the important point. Now students, our equation, let us consider the flow of a compressible fluid through a varying area passage with a subsonic velocity. So students, let this be a converging passage. Okay, converging. So flow is taking place this. So at inlet, let the condition of flow, let the flow be subsonic. So subsonic means here Mach will be less than 1. Okay, Mach will be less than 1. Since here dA by A is negative, because area is decreasing. It is a converging conduit, right? So students, our equation relating dA by our equation for dA with respect to velocity, which is the equation? So this is our equation. dA by A equal to m square minus 1 into dV by V. So here dA by A equal to m square minus 1 dV by V. So students, our m is less than 1 means this term will be, what will be the term? What will be the term? It will be negative. M square, this term will be negative, right? And this term will also be negative. So this term to be negative, if dA by A has to be negative, then naturally dV by dV must be positive. Positive into negative will be negative. If dV by V was negative into negative, it will become positive, right? So here this means if m less than 1 and dA by A is negative means gives dV by V will be positive. what is the meaning of this statement? If in a converging section, if at the inlet the condition of the flow is subsonic, then the velocity of the fluid will increase. So it will act as nozzle. So it will act as a nozzle. So for nozzle, the nozzle should be converging. Nozzle should be converging in shape. If the inlet condition of the flow is subsonic. Now I will consider the same converging type conduit, and Mach here is greater than 1, and dA by A is negative itself. dA by A is negative itself. So what will happen? So dA by A equal to Mach square minus 1 into dV by V, right? So if dA by A is negative itself, Mach square minus 1 will be positive because M is greater than 1. So if this is positive, dV by V should be negative. Then only this will be negative. So it means here the velocity decreases. But velocity decrease means it is not a nozzle. For a nozzle, if the component has to be a nozzle, the velocity should increase. So this is not a nozzle. Then what is this? This is a diffuser. Because in diffuser velocity should decrease, pressure increases. So if you use the equation for pressure, you can see that pressure increases. So students, important thing, if area is converging, if m less than 1, it will be nozzle. If m greater than 1, it will be diffuser. Okay. If m less than 1, it will be nozzle. If m greater than 1, it will be diffuser. A converging cross section acts as nozzle only if at inlet the section is at inlet the flow is subsonic condition. When the flow is supersonic condition, that is m greater than 1, it acts as diffuser. Now I am taking a diverging section. So at inlet m less than 1, that is subsonic condition. So dA by A equal to m square minus 1 dV by B. So here dA by A is positive because it is diverging. So naturally here m square minus 1 will be negative. dA by A is positive. So this to be positive, a negative should be multiplied with the negative itself. So dV by V is negative, means velocity is decreasing. So velocity decreasing means it is a diffuser. It acts as a diffuser. So if Mach number is less than 1 in a diverging section, at the inlet of a diverging section, if Mach number is less than 1, means it is a diffuser. Okay, it is a diffuser. Now same a diverging section at m greater than 1. So dA by A is positive. So dA by A equal to m square minus 1 dV by V. So this will be positive because m square minus 1 will be positive, m is greater than 1. And this is also positive. So in order to maintain, in order that dA by A should positive is, it should be multiplied with the positive itself. So dV by V is positive. Means velocity increases. Means it is a nozzle. So students, a diverging section acts as nozzle only if at inlet the condition of the flow is supersonic. For supersonic flow, diverging section acts as a diverging section acts as what a diffuser. Sorry, nozzle. So a diverging section acts as if m less than 1 means diffuser, m greater than 1 for a diverging section means it is a nozzle. Okay, so this is the difference. This is how so students, you might have thought that only decreasing cross section will enable the flow to increase its velocity. That is very wrong. It not only depends upon area, it also depends upon the Mach number of the flow. If a converging conduit or path only a converging conduit acts as a nozzle only if the inlet condition of the flow is subsonic. If it is supersonic, it won't act as a nozzle, it acts as a diffuser. So that is the main difference. So very important concept, you have to be thorough with this concept. And another case, so here in case of nozzle can be of two types. Both converging and diverging can be nozzle. Okay, so here m should be less than 1, here m should be greater than 1. The flow is in this direction. So at inlet m should be greater than 1 here. At inlet it should be m should be less than 1. So what about m equal to 1? What happens when m is equal to 1? So students, dA by A equal to m square minus 1 dV by V. So if m equal to 1 means this will become 0. So give dA by A equal to 0 means A is constant. A should be constant. Either A should be maximum or A should be minimum. So if A remains constant means it has reached the Mach number 1. So when a flow Mach number is unity, both the equations require dA to be both the equation means the equation of velocity or equation of pressure, dA will become 0, which means that the location where the Mach number becomes unity, the area of passage must have either a minimum. Mach equal to 1 means area of passage either have a max or minimum value. Okay, so students, basically if this is a conduit with the insulator conduit, so here it is converging means it acts as nozzle. If here it should be m should be less than 1, here almost constant, right? And here m should be greater than 1. So since this is diverging, so initially converging means here m is less than 1. M is less than 1 means the velocity is lower than the acoustic velocity. Since it is a nozzle, its velocity increases means its Mach number becomes 1. If Mach number becomes 1 means at certain spot it should have a area should be constant, and after sometimes velocity again increases means Mach will be greater than 1. When the Mach becomes greater than 1, naturally if the conduit is to be maintained as nozzle itself, then the section should diverge. Otherwise it will act as a diffuser, right? So in order to make it as, so here it is Mach equal to 1. In order to maintain the component or device as nozzle itself, the section will diverge. So this is how a nozzle looks like. So similarly, so this is a converging diverging nozzle. Converging diverging nozzle. Combination of both. Combination of both. So similarly, our a diffuser can also be a converging diverging diffuser. Converging diverging diffuser. So students, what should be here? So if this is the flow direction. So initially it is converging. Initially converging means for a converging conduit acts as diffuser only if inlet Mach number is greater than 1. So inlet Mach number is greater than 1 means it acts as diffuser. Since it is acting as diffuser, slowly velocity decreases. Velocity decreases and at certain point velocity decreases and or Mach number decreases. Mach number will reach a point where Mach equal to 1. So at a Mach equal to 1, the area the conduit's area, the cross section area should be a constant or maximum or minimum. So here it is some constant values obtained, and and again velocity decreases, and it will the Mach number will get reduced or lower than 1. So after the Mach number's value get reduced less than 1 means it has reached subsonic value. So the if the device has to be maintained as diffuser itself and our condition has become subsonic means and its cross section should start to diverge. So here m less than 1. So this is a converging diverging diffuser. So this is explanation for shape of diffuser or shape of nozzle. So students, you have to remember the facts that nozzle can be converging, nozzle can be diverging, nozzle can be converging, diverging based on the flow conditions or the flow Mach number. Similarly, diffuser can be converging, diffuser can be diverging, and diffuser can be converging, diverging based on the flow Mach number. Very important. Okay, so the equations by the governing equations for the shape of the nozzle and the diffuser are these equations. Which one? Either this can also be used, or dv by this equation can also be used. This can be also used. I have used this particular equation. Okay, so I have studied only the change in velocity with the change in area. You can also use this equation, change in pressure with the change in area. So here pressure is related with the area and it is also a function of Mach. So here it is 1 minus Mach. Here it is here Mach minus Mach square minus 1. Okay. So that's all. That's all for the today's session. Thank you.